Welcome. My name is Randy Ellis. In this session, we'll look at some prerequisites for our course, and specifically, we'll look at some of the properties of a vector. So the main concepts in this session are a vector for us is a column of real numbers, a finite column specifically. We'll look at how you can scale one vector and how you can add two or more vectors. We'll explore what a vector norm or magnitude means with a couple of specific examples. We'll look at the dot product, which is one form of the vector inner product. We'll see what it means for a pair of vectors to be orthogonal and for one vector to have a unit magnitude. We'll look at linear combinations of vectors. And we'll start off by saying what a vector is. So for our computational purposes, a vector is an ordered list of real numbers. The set of real numbers is written as this script R, and so what we have in computing is a finite list of these. Some vectors in mathematics might be over a different field. Here, the field is the real numbers. And it will say if it has m entries that it has size m. In some areas, we'll use the term dimension, but dimension won't be, in our terminology, used for a vector. It will be used for something else. We'll write a vector as an ordinary script letter, usually from the start or the end of the alphabet, with an arrow over it, and we'll say it's a member of the m-dimensional real numbers, which is to say that the vector has m entries, and these entries are all real. An example that you're probably already familiar with is the plane, which we'll say is r2 or r squared, and here a vector has two entries, and we'll indicate the entries by using the same letter as for the vector and a subscript indicating the entries. So here it's v sub 1, v sub 2, sometimes we'll say v1, v2, although that's an ambiguous term. A vector has a couple of important properties. One is that you can scale it, and specifically in our case you can scale it by a real number. What that means is, suppose alpha is some real number and a vector has m real entries. What that means is that alpha times v is a vector. A counterexample is when you use a real number as a code for something else. We call this a categorical variable. So for example, suppose that you're referring to people and you're saying that people with height less than 2 meters get a code of -1, and a person whose height is at least 2 meters gets a code of +1. For reference, I'm a -1. So you can't scale this number by 0.5. For example, if the entry is -1 for height less than 2 meters, -0.5 has no meaning. So the semantics of the entries cannot be changed by multiplication by a real number. That's the essence of this. And what we also say is you can't have categorical values. The way that we'll represent a vector is quite specific. In mathematics, there isn't any strict rule for how a vector is to be represented. For us, because we actually have to perform computations, we have to settle on a representation, and what we'll do is we'll represent this as a finite column of real numbers. So if there's a vector with m entries, we'll have a column, and it'll be v1, v2, v3, and vm. You're probably already familiar with the idea of a transpose, and the transpose of a vector to us is a row, and we will write this as v1, v2, v3 to vm, and now they're all lined up in a row. Two vectors can be added. Suppose that we have two vectors. One vector is u, one vector is v. Each of them has m real entries. We can define the sum of these as being the first entry of the sum is the sum of the first entries, the second entry of the sum is the sum of the second entries, and so on until we've used up all of the entries in u and v, and we have the nth entry of the sum. Again, you're not allowed to have a categorical value as an entry. So for example, if the last entry was trying to code for height, 1 plus 1 is 2, and that makes no categorical sense in the coding that we're looking at. A vector norm is a way of measuring a vector. It's a single real number, so it's in the set of real numbers, and it's written using double bars around the vector. An example that you already know is the absolute value, which is the way of measuring a single real number. A norm in general satisfies 4 mathematical axioms. You might say that a norm has 4 properties. The first is it has to be non-negative, so it can be 0 or any number up from 0. A norm is 0 if and only if every entry is 0. What that means is if the norm is 0, then every entry is 0, and if every entry is 0, then the norm is 0. If we have a real number and we use that real number to scale our vector, then and take the norm of that scaled vector, then that has to exactly equal the norm of the vector times the absolute value of that real number that we're using to scale. If we take the two vectors and we add them together and we find the norm, that has to be less than or equal to the sum of the individual norms. This is sometimes referred to as the triangle inequality. You can think in a plane of a triangle, and what that says is that if you take two legs of the triangle and add up their distances, that the length of the third leg cannot exceed that. Another word for vector norm is a vector magnitude. There are two prominent norms that we'll often use. The first one is so usual that we often don't include a specific subscript, and it's called the Euclidean norm. It's also called the L2 norm. And this is defined as the square root of the sum of the squares of the entries. So this is probably familiar already to you from geometry. And the L1 norm, which is one that is somewhat less common, although it's very common in data analysis, is the sum of the absolute values of the entries of the vector. There are two prominent norms that we use when working with vectors. One of them is so common that we often drop its notation. It's formally called the Euclidean norm or the L2 norm, and it's very, very common. Often the subscript will be omitted and we'll just use the double bars. The way that we'll define this is the L2 norm or Euclidean norm of a vector is the square root of the sum of the squares of the entries. So this is what you would get in ordinary 2D or 3D geometry. Another norm that's very useful in linear algebra is called the L1 norm, and it's defined as the sum of the absolute values of the entries of the vector. The inner product of a vector of a pair of vectors is a linear function of them. And in general, it's written using these angle brackets. The one that we'll use is most commonly called the dot product, and it's written in infix notation. That means the operator is inside the symbols, and this is u dot v, or the dot product, or the simple linear product. This is defined, the dot product of vectors u and v is the sum of the products of the respective entries. So this would be u1 v1 plus u2 v2 plus u3 v3, etc. up to um vm. What we observe is that because scalar multiplication is commutative or abelian, that means that this is a commutative or abelian operator, so we can write u dot v equals v dot u, and then using the transpose, a compact way of representing the dot product is u transpose v. Now, vectors can be orthogonal, and a single vector can have a unit magnitude. If two vectors u and v, both having m entries, are orthogonal, what we mean is that the dot product of the two vectors is 0. A unit vector is a vector that has a magnitude of 1. So incidentally, v dot v is the sum of the squares of the entries, so the L2 norm is just the square root of the dot product of the vector with itself, and that is unity. A set of vectors can be both. Suppose that we have a pair of size 3 vectors, and we can observe for, I'll just work with this one first, is that let's look at its magnitude. So 1 over root 2 times 1 over root 2 is 1/2, 0 times 0 is 0, 1 over root 2 times 1 over root 2 is 1/2, 1/2 plus 0 plus 1/2 is 1, so this is a unit vector. Similarly, this is a unit vector, and with their dot product, the dot product of these, the product of these entries is 1/2, 0, minus 1/2, so 1/2 plus 0 plus minus 1/2 is 0, so that means that these are each unit magnitude and orthogonal vectors. There are some special vectors that we use, and in particular when we have a vector with m entries, we'll often use two of them and occasionally use a third. The first that we'll commonly use is the 0 vector, and the 0 vector has 0 in each entry. The 1's vector has 1 in each entry, and by the way, if you're using MATLAB, there are very easy ways to create these. The elementary vector is something that we won't use often. We'll sometimes use that symbol E for a different purpose. For these prerequisites, we'll think of it as the elementary vector. And the elementary vector for a vector with m entries means that the jth entry is 1 and every other entry is 0. Let's look at the three kinds of special vectors that we have. So here we have the 0 vector. Here we have the first elementary vector. Here we have the second elementary vector. Here we have the third elementary vector. A linear combination is an important concept in linear algebra. Suppose that we have n vectors and each one of them has m real numbers. Suppose that we have m of these scalar values, we'll call them the weights, and suppose that there's another vector that's also has m real entries. The weighted sum of these is we take the first vector times its weight plus the second vector, scale it by its weight, and so on, and then add all of these up together, and we'll say that C is the weighted sum. So that's one term that we'll use for this. Formally, it's called a linear combination. So let's go through an example here. Suppose that A1 has some real number in its first entry and 0 in its second entry. Suppose A2 has a possibly distinct real number in its first entry and 0 in its second entry. And suppose that the vector C has a possibly distinct real entry and it's got a 1 in its second entry. There's no linear combination of A1 and A2 that will produce C. And that's because every time we multiply a weight by this second entry and then a possibly distinct weight by this entry and add them up, we'll never get 1. So there's something distinctive about this set A1 and A2 and this new vector C. Now, let's also observe, suppose that for A1, its first entry is non-zero. If it is, we can actually compute A2 from A1, and we can do that by scaling A2 by the ratio of V and U. This leads us to the concept of linear dependence. Suppose now we'll call that set of n vectors A, and each one of them has m entries. Now, what we'll do is we'll put a condition on the weights and have a property. So the condition is we have a set of real numbers, and there are n of them, and at least one is non-zero. This is an important thing. We'll say that W is a non-trivial set of weights. And if we have a non-trivial set of weights and we add these up, then, and so we take the weighted sum of all of the vectors, if we get the 0 vector, we say that the set A is linearly dependent. So an example of some linearly dependent size 3 vectors are our previous examples of these unit orthogonal vectors and the first elementary vector. Let's just consider what happens if we multiply this by let's say root 2. If we multiply this by root 2, it's 1. If we multiply this root 2, it's 1, and the sum of them would be a 1. If we multiply that by root 2 and that by root 2, we get a 0. And then if we multiply this by root 2, we get minus 1. This by root 2, we get minus 1. So we get plus 1, and that would add up to 0. So the weighted sum of A2 and A3 would be 2, 0, 0. And if we then multiplied A1 by minus 1, we would get the 0 vector. So that would be a simple example of how these 3 vectors are linearly dependent. Now, we actually have computational ways that are quite efficient and effective for determining if they're linearly dependent, but that's something that we'll go through later in the course. A closely related concept is linear independence. Now we'll have a set, it'll be the same setup. We have a set of n vectors each one of them having m entries. And for it to be linearly independent means that for any non-trivial set of weights, we never can create the zero vector. So this is not exactly the reverse of linear independence, but it's a complementary concept. So in this case, linearly independent, if we have these two unit orthogonal vectors, and now we have the second elementary vector, this is forming a linearly independent set of vectors. So what's the summary for this prerequisite session? Vectors, suppose we have two vectors, they each have m entries, they're represented as columns for us, and each one of those entries is a real number. We can scale a vector by a real number. We can add two vectors that have the same size. Special vectors include the zero vector and the one vector. A vector norm is a way of measuring the magnitude of a vector using a non-negative number that has certain properties. Unit vector is one that has a magnitude of 1. The dot product of a pair of vectors is represented using an infix notation. If we have a non-trivial linear combination of vectors, they're dependent if some non-trivial linear combination is the zero vector, and they're linearly independent if no linear combination produces the zero vector.